The next presentation is by Benoit Hamelin, Vector Space Embeddings and Data Maps for Cyber Defense.
Wait until the talk is started. Thank you very much, Inessa. Before we begin, a few words about us and the Todd Institute. So we are a small research department within an organization in Canada that is part of the intelligence community, and one of its mandate is about developing expertise in cyber defense. And as we're about to see, while cyber defense seems like a very humdrum, very IT kind of thing, I feel that doing it well requires a lot of science, so let's start digging in. So let's say a few words about what it is first. It's many things, but at the end of the day, it's about defending a form of ownership or a certain form of guarantee around who gets to see your data, who gets to change your data, and when your data can be seen or changed. There are many things that can happen within an IT infrastructure where this data can be accessed and modified, and we are doing our best to keep those guarantees intact. A sort of flip side of detecting threats to confidentiality, integrity, and availability is finding the traces that can go back to events where those properties have been breached. So the name of the game is monitoring. You want to look at where your data is stored, how your data is used, and monitoring involves deploying plenty of sensors into your networks, and those sensors bring back telemetry. Analyzing the telemetry gets you to, of course, know your infrastructure, but know it into details, not just from the perspective of how you've built it or how you're using it, but really how it is being used by all the users, all the applications, all the business functions that are going on it. And on the flip side, when you know very well your IT infrastructure and resources, you can go beyond the known normal activity and perhaps find the traces of malicious activity. Okay, yeah. Before I go about the volumes of telemetry, let's go into the notion that there's not just one sensor to rule them all and inform us on what's going on. We have to look at the IT infrastructure from multiple perspectives. And I'm listing a few of those here. All of those get centralized in the same places. They tell different stories about what's going on. And today, together, we'll be looking at one particular type of telemetry that we collect and analyze, and that's the command lines that support processes. In particular, I'll be showing a few examples of wrangling this telemetry into an analysis framework using an open data set that's been produced by my colleagues at the Lawrence Livermore Laboratory. So they have been developing a research so-called host-based agent. It's a program that sits at the boundary of the operating system's user mode and kernel mode and just watches events going on the system that have value with respect to retracing malicious activity. So it will observe in particular the life cycles of processes running on the machine, the moments where programs start and stop. And attached to each program instance, each process instance, you have the command line that describes how to run that program. And the nice fact about command lines is that it's one of the data artifacts that we collect that is the most direct link to the intention behind running the program. So this gets us, in some cases, back to why the program might be running at that moment and in that place. Don't let yourself be fooled by this tiny, tiny data set. Okay, 140,000 process instances is absolutely not reflective of the, it's not petabytes like the LHC project, but too much data to be able to easily wrangle together, yet our tools enable at-scale processing of telemetry. So there's a key constraint in our analysis frameworks, and it's the fact that we don't know really what is going on. We just see the data itself. It is never paraphrased by supplemental information guiding us into what it means, why it is being generated. It's all first-degree literal. In statistical parlance, there is no label to support the interpretation or the causality interpretation of the data. So we're stuck doing unsupervised analysis of the telemetry. We have to take it for itself and look at patterns of similarity that occur in the telemetry stream through the exercise. Now, when you look at telemetry that way, every approach that you develop is one perspective you take on it. Think of it as one lens to put behind your eyeballs and look at the telemetry. Each of these representations, each of these lenses tells a slightly distinct story, and it's by putting these stories back together that we get a fuller appreciation of what goes on in the network. To torture some aphorisms, one could say that all lenses are wrong, but some are useful. And a useful lens will provide us with insight, enabling taking difficult decisions about things to take offline, documents to back up, various other incident response actions to take, and it will also help with labeling the data for prospective data analysis or other future concerns. So we have developed a pipeline for processing this data into insight. It involves a bunch of libraries and packages that we have developed and released as open source. So essentially, the various steps to insight from the data is to first turn it into vectors. Then we compress those vectors into low-dimension representations that are suitable to visualization and density-based clustering. Then we look at them interactively, looking for interesting clusters, looking for interesting non-clusters, and eventually, after doing some interactive labeling, after identifying strongly reliable phenomena that interest us, we can leverage scikit-learn and other incumbent supervised learning tools to learn to detect those at scale. The end goal of our analysis that we'll be looking at today is called a data map, and it's a figure here as I'm showing. Essentially, a data map shows 1 point for each object in the data set you were looking at, and it brings them together if those objects in their original form satisfy a certain notion of similarity. And for people, hey, wait, do you guys see the image? There's the image. And for the record, this is done with matplotlib. So not all the slides are, but the images are. So how do you make one of those lenses? As we've seen, there's a linear recipe to get to it, and most of it involves, at least in this talk, this vectorizers library that we've been releasing. So now, this is not to say that vectorizers should replace all the things. Rather, if your data is text, if it's images, if it's videos, there's plenty of perfectly fine vectorization models that are out there, and you should use them. The thing that vectorizers do is it fills the gap when there is such a thing. And in particular, it is good for turning into vectors data that is naturally formed by variable length sequences of things when those things are also categorical values. So, in this case, I said we will look at command lines. Command lines take the form of strings, so we have a sort of text analysis problems. Let's turn our text into vectors. So if you were data science practitioners in the 2000s, you might be familiar with building bag-of-words models as prehistoric NLP kind of approaches. And such approaches are super useful in cyber defense. Here, let me take our command lines and use the shlex module from the Python standard library to cut them into tokens. Those tokens become the points around which I consider similarity between command lines. This maps my strings onto a vocabulary of categorical values. Code to do this, we are shamelessly stealing the idioms of the scikit-learn package. Therefore, it should all be familiar except the class names change. So if you look at the sort of math that supports a bag-of-words model, essentially this is just a counting game. Okay? You take every one of your token sequences, you count them, it forms a matrix that if you have strictly one occurrence of any token in your sequence, it's a one-hot encoding. If it's more, then it's a generalization thereof, you have counts. Now, a known problem with bags of words is that they are very sensitive to the occurrence of so-called stop words. Take any sequence of documents in the English language, and you will find very few that don't have the word the in them, right? So are all documents similar thanks to all having the word the in them? No, not really. The word the does not give you much information about the purpose or the object of the document. So we have developed a thing, consider it a theoretically well-founded TF-IDF that is called the information weight transform that will reweigh our count matrix in order to make the informative features more salient for each record. Once again, code for doing that is scikit-learn-ish. There is math. And then we finally have large dimension vectors for these. How large? Well, I have in this data set some 30,000 command lines, and they get expressed over a humongous vocabulary of, hey, how come this is not following? Okay. And vocabulary size is about 20,000. Having this sort of ratio of having closing on to one-to-one token per object means that you have lots of fragmentation in this vocabulary space. So we cannot expect to have the greatest performance from this, yet it's the simplest model, the bag of words. Let's go and take a look at what it gives us, if only a straw man that we can then beat. So the math. And then we can talk a little bit about UMAP. It is the way by which we compress our 20,000 dimension vectors into 2D vectors we can take a look at. So why UMAP? Because UMAP will unroll the latent manifold on which your high dimension points reside in the process of projecting them down to 2D. UMAP does the best job it can to preserve the local similarity structure between the points. That local similarity structure that exists in the high dimension. Yes. Again, scikit-learnisms. Since we're counting things, there's a good math theory that says you should use Hellinger distance as a metric between those things. And here we go, we get a data map out of that. Put on your opera glasses and pay attention to the points on there. You may feel like, yes, there is some clustering, but there's also some good spread of the points. This is the fragmentation of space that comes from having a vocabulary that's a little too big. So can we do better from this? Yes, mesdames and sirs, we can. Think about it. If you take any one of those command lines you have, you can't just reorder the tokens any way you want. Order of tokens is important. Another way to see that argument is that tokens are not independent, right? They come into a certain order, and if anything, the occurrence of a certain token depends on the occurrence of another one. There is a sort of causal relationship that goes both ways along your sequence. So, okay, let's take another stab at this, where we can have command lines being distributions on point clouds. Okay, so these are words, right? So the plan here is the tokens themselves, we will project them into a vector space. Now, the same way that we have documents being a count of tokens, we can have them being counts of vectors, right? Or, more generally, distributions on a point cloud. Now, distributions on a point cloud, there exists a metric to measure the distance between those. It's called the Wasserstein distance, or the Earth mover distance. And thanks to this metric existing, we can pivot from distributions on a point cloud to a vector space embedding. Okay, so tokens as vectors. You can do that, again, with a scikit-learnism, by considering co-occurrence of tokens. Okay, so essentially you're saying two tokens should be similar, should be close in a vector space if they occur together along the command lines where they occur, right? More than that, they should be closer together if they have the same sort of causal relationship between them. So thanks to math, we can do this embedding, and here's a 2D representation of that token embedding using UMAP. We see we're not doing that in vain. Do you see my, yeah. So my arrow is pointing here at those clusters of things. So there are many tokens that really just come together. It makes no sense to take them separately from each other. They co-occur almost systematically. A tiny look at the legend also shows you that analyzing command lines is a pain in the butt. Most of the tokens that we see are base 64 encoded serializations of complex data structures passed on to programs. So having a system by which we can extract some sense out of this is useful. Okay, moving on. We have a vector space of tokens. Now, let's represent those as distribution. Let's represent the command lines as distributions over that vector space, and let's compare them. So we do that thanks to a method called Wasserstein vectorization. Here's a paper reference. Again, we can crunch that using a scikit-learn-like idiom, and you see that now each process, or rather each command line, being a distribution over point cloud of token co-occurrence vectors. More math supporting that. Essentially, topology gives us tools to map the distance between point clouds. More cogently, you measure the distance between each point cloud to a reference distribution, and that allows you to compare all of those on a common basis. And thanks to that, we get a vector space embedding. And here's a comparison between good old simple bag of words and this much more sophisticated analysis that, not analysis, but embedding that we just crunched. And we see that it solves many of the spreading problems. Again, put on your opera glasses. Look at the little blue dots here, right? In the middle, the label for them is msh.exe. So these are my browser command line instances. And with the, with the bag of words model, we see that it occupies a large number of distinct tokens, and as such, it forms a vague cloud of circular structure in the map on the left. And all that spurious spread gets cinched up and brought back together in the Wasserstein vectorization of command lines. There's other such good properties of processes that I have a strong assumptions should be similar in their purpose, getting lined up into tighter clusters thanks to this more sophisticated method. So from that, we can explore this data map. We have this package called data mapplot. I used it to generate the static images we've just seen. Okay, there's code. And then you can take a look interactively at this projected in a DeckGL backend. So you can zoom in, zoom out, move in and move out, hands up, hands up. And then another thing you can do with that is, wait, why are my images disappearing all the time? Here, okay. Another thing you can do with that is use another library you've been developing called this, not that. I have similar naming proclivities as Mrs. Barnes. This enables you to build interactive labeling dashboard applications that live directly into a Jupyter notebook thanks to panel library. So you need a little bit more code, but if you do pay the price, you get something like this. When you select a cluster of points, you get to interrogate using various tools why these guys are coming together, what they have in common, and then you get to name them, and that naming thing is the insight. It gets documented, stored away, and is usable for the future. And then once you have those labels, predict them, and on the other side, whatever you can't predict becomes an anomaly. It is interesting unto itself. I would be remiss not to mention that we can have alternative lenses, right? We're just telling one stories using command lines, and it's worth telling more about the way processes are similar to one another. One of those lenses is by looking at the shared code libraries that processes might share, right? Might have in common as they are instantiated. Another thing that you can do is say, if a process is a bag of command lines, well, a host is a bag of process executions. And now you can look at hosts in how similar they are in their application workload and do that over time. What I'm showing to you here is the uncomfortable bleeding edge of our research. We're not very good yet at using 3D imaging, but that sort of analysis, and we're using awkward flattened imaging like this. During the sprints, Tetsuo Koyama said that he would help me try and wrangle some PyVista in order to do that right. Okay, so closing. We have a recipe for building these tools that get us insight on the way that networks behave in a way that before you had to put all the data in a spreadsheet and play pivot table games until your eyes bled. That process involves first turning your data into vectors, and we have tools for when your data won't fit the things that already exist in the community. Then you crunch that data into 2D and you look at it until your eyes bleed. And once your eyes bleed, use scikit-learn and be happy. The whole thing, I've gave it in snippets. I won't say it looks easy to do, but if you've used scikit-learn, it should at least look vaguely familiar, and I hope that by summarizing it here in 10 lines of code, I can convince you to at least give it a little try. We're the Todd Institute. We do all sorts of packages for doing unsupervised analysis of code and visualization of those things that we put together. And if you are interested in redoing the experiments that I've just showcased in this talk, please take a look at this. The Acme dataset is open, it's easy to download, and all my code you should be able to run this on a small to medium notebook with not too much trouble. Thank you so much for your attention.
Thank you so much, Benoit. And now it's time for questions. Do we have any questions from the attendees in the room? Okay. I see one hand up. I'll come up with the microphone.
Who?
Just shout and I'll repeat it.
First, I just want to say thank you. Really informative. You mentioned a lot of different types of telemetry data. I think we looked specifically at the command lines. My question is, for all those different types, how do you kind of marry those together, and does that help provide more insight? Is it the same pipeline done across those? I guess, how do you get all that information together to look at the various lenses, as you mentioned?
It's a question that's also part of our current agenda of research. If you do the naive thing and just combine the vectors from different perspectives that describe the same object, essentially it's like applying an AND logical connector between two similarity predicates, right? So the clusters that will remain from analyzing this data are the things that satisfy all the similarity notions at the same time. And the interesting phenomena, the things you have to learn about, the baseline behaviors of your network and the cockroaches crawling underneath, it's not necessarily things that satisfy all the similarity criteria at the same time. So combining those stories otherwise than by human insight and joint interpretation of two disjoint plots, we're not too sure yet how to do it, and the naive approach is not that useful. Another thing that comes up when you do the naive, say, concatenation of all the vectors describing the same thing is, well, you never have a perfect one-to-one mapping between objects, so you reject all those that you can't do the combination, so you're dropping data on the floor. And what you mostly get as a result, as a clusters that you will find, are predicted by the volume of repeated data points. So, yeah, I don't have a satisfying answer to this one.
Thank you, Benoit. Do we have any more questions in the room? I have one question through Slack. Any questions in the room? A question from Eric Ma. Is Wasserstein distance only 1D?
Wasserstein distance, not only on 1D. So So maybe I'm interpreting the question wrong, in which case come see me out of bounds. But right now, we measure the Wasserstein distance between collections of vectors, well, rather weighted collection of vectors. And we measure all of these to a reference distribution. So no, it's a generalized computation of the Wasserstein distance that involves the actual resolution of a linearized version of an optimal transport problem.
Thank you, Benoit. We have one more question from Evelyn Salmon. How do these vector embeddings compare to pre-trained language models like BERT?
So we have done lots of experiments with actual text data in addition to telemetry. So we have pretty good data on this. If you go to the Read the Docs page for vectorizers, there is actually a benchmark that compares the performance of the Wasserstein embedding of the 20 news group network to a BERT version or S-BERT version that was the thing 2 years ago when that thing was written. And it turns out that the Wasserstein embedding is competitive, although not winning. But it means that even if you don't use a state-of-the-art NLP model for vectorization, you still get pretty good mileage in general, and to us that was encouraging.
Thank you, Benoit. This was the last question for this session. Let's give a round of applause to Benoit.